So we have two more talks before we have the poster session. And the next speaker is Lane from Carnegie Mellon University, and going to talk here about rank-based models and how they connect to SPDEs.
Thanks, Savannah. And also thanks to the organizer for accepting my contributed talk. So I would like to talk about rank-based models with common noise and how they are related to a notion of solutions. Oh, I'm sorry. It's on green.
It's on green?
Like this?
Yeah, it is.
Okay.
Yeah, test it out?
Testing. Is it on?
Yeah.
Oh, okay. Maybe. Is this okay? It's okay. Sorry. Yeah. Okay. And I'm going to talk about rank-based models and how they are related to solutions for SPDEs called pathwise entropy solutions. And this is based on joint work with Misha Shkolnikov. So I'm going to first start by motivating the type of model we'll be considering from a financial perspective. So more specifically, we'll be looking at the capital distribution curves in stochastic portfolio theory. And then I'll introduce rank-based model with common noise, which is the main model we'll be looking at in this talk. And then I will introduce pathwise entropy solutions, and I'll discuss how they arise naturally as limits of rank-based models with common noise. And then I will state our main results and then discuss a little bit about the proof. So in stochastic portfolio theory, one thing people are interested in is how capital is distributed across companies of different sizes, and also how what's the implications for investments. And so here, in this picture, we see what's called the capital distribution curves. So each line here in the picture represents a point in time, and it plots how it plots the market capitalizations of different companies in the US, ranked from the largest company on the left all the way to the smallest company on the right. So recently, Apple surpassed Microsoft and became the largest company, and its market cap is around 1 to 2% of the entire US market. And then the second comes Apple, so on and so forth until you get to the smallest company in the US. And what's remarkable about these curves is that it's quite stable over time, as we can see. And also the top part of the curve, so representing the larger companies, this is sort of linear, which translates to a power law decay or Pareto distribution, because we are plotting this on the log-log scale. And there's plenty of literature in economics explaining why this is the case. So this is the capital distribution curves. And how can we capture what we observe, the shape of these capital distribution curves in a model? Well, to this day, the simplest such model is still the rank-based models introduced in 2005 by Banner, Fernholz, and Karatzis. And this model is described by this system of SDE here. So XI here represents the logarithm of the market cap of the ith company. So it's a real value stochastic process. And we drive it by an independence Brownian motion BI. And also B and sigma are the drift and diffusion coefficients, which represents the growth rates and the volatility of the ith company. And we make them so that they depend on the rank of Xi. So nu n here denotes the empirical measure of the particle system, and F denotes the corresponding CDF. And so if we evaluate F at Xi, we get a number of the form K over N, where K is the rank of Xi from the bottom. So this is the rank-based model. And the reason why they are able to capture what we observed in the previous slide is because if we write down the rank market rates, so denoted by mu K here, in terms of the rank market caps, we see that they depend on the gaps between the market caps. And this process is actually a reflective Brownian motion, which is a well-studied Markov process. And so we know quite a few things about its stationary distributions. So in particular, the stationary distribution of the ratio between successive rank market rates follow the Pareto distribution. And so if we plot the log-log relationship between the market weight and their ranks, it indeed reproduces the shape of the capital distribution curves we saw previously. So this is this rank-based model are able to capture the static behavior of the capital distribution curves. But for investments, we are also interested in the dynamic behavior. So how the curve fluctuates over time, so that we know, for example, how we should rebalance our portfolio. And understanding the dynamic behavior is quite a bit more complicated than the static behavior. But this can be first done by understanding the large N limits of the rank-based model. So in other words, corresponding to the case where there's a large number of companies. And this is reasonable because we are thinking of an institutional investor. So their portfolio consists of hundreds, if not thousands, of companies. And so this was done by two papers by Shkolnikov and Jourdain and Regnier, where they show that the empirical CDF, F nu n, which describes how capital is distributed at different times, converges as n goes to infinity to this PDE in U here, which is in fact the porous medium equation. And capital B here denotes the antiderivative of little b, which in other words is the aggregate growth rate up to a certain rank. And similarly, capital sigma is the antiderivative of sigma squared over 2, so the aggregate volatility up to a certain rank. And so if we come back to our financial perspective, what this result suggests is that we can approximate F nu n, which describes the evolution of the fraction of companies with capitalizations below a certain threshold by this porous medium equation here. Okay. So this is good. But if you think about it, this approximation is not so ideal in some sense because the dynamics of this porous medium equation is in fact deterministic. And so trying to approximate the random fluctuations by something deterministic is not so satisfactory in some sense. And so the next natural thing that one might try is a central limit theorem. So in other words, studying how the empirical CDF concentrates or fluctuates around the deterministic limits U. And this was done by a paper by Coley and Shkolnikov, where they show that if you scale the difference between the empirical CDF and its deterministic limits U by square root of n, it converges to a random limit G, which solves this SPDE here, and is in fact a Gaussian random field with tractable mean and covariance structures. So again, coming back to the financial perspective, what these two results suggest is that together we can approximate the empirical CDF to the fluctuations of the market by the sum of U, which is deterministic, plus a random quantity here, 1 over square root of n times G. And it turns out that this approximation works well when n is large, but not super large. So for example, when n is of the order of 100, we can indeed calibrate the fluctuations of the actual market to this approximation. But when n is very large, this approximation breaks down because of the 1 over square root of n in front of G, which implies that we still have little randomness left when n is very large. And so a natural remedy for this, which leads to the main model of today, is to introduce some common noise. So in other words, some common source of randomness driving all the log caps. So here, this common noise is represented by a Brownian motion W, which influences all the log caps xi. And we also have a coefficient in front gamma, which is again rank-based, so acting on the rank of xi. And so this is the rank-based model with common noise. And the question that we wish to address is the same as before. Can we say something about the dynamic behavior for this model with common noise for large n? And unlike these idiosyncratic noises, the common noise term is expected to survive when we send n to infinity, which gives us the desired randomness in the limiting market dynamics. So we wish to find out the large n limits of this model. And if you look at this, this system here is in fact of mean field type, because the dynamics of xi depends on the other particles only through the empirical measure un. And so we can apply the usual McKean-Vlasov heuristic to guess what the limits may look like. And on the level of the CDF, McKean-Vlasov heuristic suggests that it converges to U, which solves this SPDE here in U. So if we ignore the last term, we have the force medium equation that we saw. So this last term here comes from the common noise we added, and G here denotes the antiderivative of gamma. And this denotes the Strotanovich integral. And this SPDE was studied in a very nice paper by Guess and Tsouganides in 2017, where they introduced an appropriate notion of solution called pathwise entropy solution, building on earlier work by Lyons, Pertam, and Hoffmanova. So let me now describe how they build this notion of solutions. So the first step is to rewrite this SPDE in what's called the kinetic formulation. So how do we do that? We introduce an auxiliary variable psi, which in our case stands for the rank. So it's a number between 0 and 1. And then we define this function chi, which is an indicator function, where we threshold our solution U against C. And if you compute the derivatives of chi formally, you will see that it satisfies this linear SPDE. So we are already looking a bit better because we have rewritten a nonlinear SPDE into a linear one. However, this brings about a problematic term, which is W prime here. Because in our case, W is a Brownian motion, and so W prime simply blows up. And so to address this, Guess and Tsouganides looks at the weak formulation of this SPDE here. So in other words, testing chi against test functions, suitable test functions. And the clever idea that they had was that we should not just test chi against all smooth functions, but rather a carefully chosen subset of test functions. So what are these test functions? They are solutions to this linear transport equation here. So in fact, this transport equation comes from the SPDE. If we go back a little bit, and we look at our original SPDE, and just ignore the second order term, the sigma term here, we see that this becomes the first order linear transport equation in rho. This one here. And the solution to this linear transport equation is given by this formula here in rho, where we let rho 0 vary over all smooth and compactly supported functions. But the arguments inside rho 0 are chosen to be in this careful manner depending on C, T, and X. So these are the test functions. And if we now test chi against these test functions rho, we get this weak formulation here. And the miracle here is that the W prime has disappeared from the equation. And the reason why this happens is because in this weak formulation here, we are looking at the weak derivative of chi times rho. And if we use the product rule to differentiate this, because we have chosen rho to satisfy this transport equation, the two terms involving W prime coming out of the product rule cancels out each other. So we end up with this formulation with every term making sense. And so we can use this as a definition. And Guess and Tsouganides call this pathwise entropy solutions. So U is a pathwise entropy solution to our SPDE if these three properties A, B, and C are satisfied. And B here is the weak formulation we just saw. And on top of it, they impose two more regularity assumptions on U. So the first regularity assumption says that U should have a density which is square integrable. So if you think of U as a CDF, it says that the measure associated with U should be absolutely continuous with a density which is square integrable. And the third regularity property C is a regularity for the change of variable for this integral on the left. So if we look at the integral, we are integrating chi times rho x, so we can ignore the sigma term. And one way to integrate this is to do integration by parts. So we can move the x derivative here to chi. Now chi is an indicator, but we can differentiate formally to get the Dirac mass of C at ux, at u times ux by the chain rule. And if we integrate out the Dirac mass, we will get this quantity on the right here. And so what this third property C is saying is that the formula calculation we just did is actually valid. And this has to do with the regularity of U. So these three properties define pathwise entropy solutions. And one of the key results in the gas and Tsukunides paper is that under suitable assumptions on our coefficients B, sigma, and G, pathwise entropy solution is actually unique, pathwise unique. So this is the main result. And so building on their main results, what we can prove is the following main theorem. So if we come back at our rank-based model with common noise, so this system of SDE here with a common noise at the back, and we look at the empirical CDF describing how capital is distributed, it converges as n goes to infinity to U, which is the unique pathwise entropy solution to our SPD. So in particular, this implies that the law of U is unique. So this is our main result, which is a type of law of large numbers or the convergence to the mean field limits. Okay, so I have a little bit of time left, so let me describe a little bit about the proof. So the main difficulty in this proof is that we need to show that any limit points of the empirical CDF must be a pathwise entropy solutions. And this is difficult because pathwise entropy solution is not so convenient for taking limits. So if we go back to the properties which defines pathwise entropy solutions, they don't hold before thinking of limits. So if you would intend to tackle this directly, you have to come up with certain approximate property of these three properties here, which seem difficult. So instead, we took an alternative route where we work with the martingale problem associated with the SPD. So what's the martingale problem? Well, we first rewrite our SPDE into an Ito formulation here. So we change the Stratanovich to an Ito formulation, which creates a extra coefficient gamma, which is the antiderivative of gamma squared over 2. And then once we have this Ito formulation, we can test U against test functions f and phi. So if we do use the Ito formula and compute what the dynamics should be, we have this here. And we can move all the derivatives to our test functions phi, and then write down the natural martingale problem by subtracting all the dt terms to the left, and then imposing that it's a martingale for all test functions f and phi. So this is the martingale problem. And it's not difficult to prove that any limit point of our empirical CDF is a solution to this martingale problem. And so the crux of the proof then lies in showing that any solution to the martingale problem is in fact a pathwise entropy solution. Because if we can do that, we can leverage the uniqueness results of gas and Tsukunides to get the law of large numbers. Okay, so to prove this key implication means that we have to show that any solution to the martingale problem must be a pathwise entropy solution. So in other words, satisfying the three properties defining a pathwise entropy solution. So let me briefly describe how we tackle each of them. So for this first property, we need to show that any solution to the martingale problem must has a density ux, which is square integrable. And this may seem like a difficult problem because in the absence of common noise, there are very few results of this regularity results of this type for McKean-Vlasov equation. But in the presence of common noise, things are a bit easier. And the way we did it was for each SDE, for each x here, heuristically, we have an SDE in time. So we can heuristically apply Ito's formula to compute du square. So we have 2u du. So u times the drift plus an Ito correction term. And if we take the expectations, the martingale term vanished. So we end up with this quantity here. And what we can do next is to integrate in space, integrate in x to get this. And now if we focus on the term on the right, we can, for the first 3 terms here, we can move one of the x derivatives to u via integration by parts. So we get this. And if we now focus on the middle term, and recall that sigma is the antiderivative of sigma squared over 2, we see that the second term is in fact sigma squared over 2 times ux squared, which is precisely the quantity we are trying to estimate. And all the other terms in the equation can be controlled. And this is essentially how we arrive at the first property. And for the second property, which is the weak formulation when we test chi against cleverly chosen test functions rho, it turns out that this complicated looking equality is also another application of Ito's lemma, but this time to this quantity here, where we integrate the explicit solutions of the transformed equation in the rank variable up to the solution u. And so if you apply Ito's lemma after a lot of manipulations, we see that we in fact get this. So this is the probabilistic interpretation of the defining property of pathwise entropy solution. And last but not least, for this last regularity property for this change of variable here, the key to prove this is the co-area formula. So if we look at the integral on the right here, we have a function of u times ux dx. So this suggests that we should make a change of variable with c being u, so that dc is ux dx. And one way to do this is the co-area formula. And the key to apply that is that we need to know our CDF is continuous. But since once we have the first property A, we know that u is in fact continuous at least for almost every t. So this is essentially how we arrive at the last property. And once we have that, we have shown that any solution to the martingale problem is automatically a pathwise entropy solution. And we can leverage the uniqueness results of gas and Pseudonides to get our law of large numbers. Okay, so I will end my talk a little early. Thanks very much for your attention.
Thank you, Lane. Are there any questions from the audience? Leonard? You're next.